Hi everyone, my name is Maxime Legoupil and I'll be presenting today my work on Iris-Wasm, the union of WebAssembly and the Iris program logic that we've used to reason formally about WebAssembly as well as some of its extensions. This is a big-ish project. I've put a list of names here of people who I've either worked with in the past on the project or that are currently working with me on Iris-Wasm, and today I'll give an overview of everything we've done, the purpose of Iris-Wasm, what we can do in the future with it, as well as go into a tiny bit of technical detail towards the end to illustrate what can be done. But I'll begin immediately with the main point of my talk, which is that I think that industrial scale language definitions should come with a formally stated universal contract backed by a machine-checked proof. So I'll go into more detail, obviously, about exactly what I mean by that. I feel like at this point, some of you might maybe agree with this, some of you might agree, but maybe have a concern about, because it's an industrial scale language, how difficult will it be to do a machine check proof on things this size? It can be done, and this is what my talk is about. We've done it, and there are certainly other examples of people doing it in the past as well. And I think because it can be done, it should be done. It's maybe useful to remind ourselves why it's interesting to reason formally to use proof assistance. I think this is going to be very, very obvious, but I think it's useful to remind ourselves. I think there are two main reasons why when you define a new language, it is interesting to do formal reasoning on it. The first is that it's going to help you find some small bugs, typos, imprecisions in the way you've presented the code, because obviously a proof assistant is very unforgiving. You won't get away with having a corner case hidden somewhere under the rug. So the proof assistant is going to help you shed light on small corner cases, typos. And of course, you need to define the entirety of your proposal in the proof assistant, which sometimes will help make things more precise in the presentation. But even if your new language already has an implementation, maybe you've run a lot of tests on it, so you're confident that you're not going to be finding any typos, I think it's still very interesting because it's going to do a lot to encourage adoption of what you've just created, both because you can now be a lot more precise about exactly what you're bringing to the table. Instead of just saying, oh, my new language is memory safe or something vague like that, you're able to have something precise defined in that proof assistant. And obviously, if you have a proof of it that is backed by a machine-checked proof assistant, it's going to increase the confidence that your proof actually is correct. But obviously, why don't we do proof assistance and formal reasoning every time? There is a huge proof burden. Anyone who's ever used a proof assistant knows that it's very time-consuming, sometimes very frustrating as well, and obviously we sometimes have limited resources and might not want to go through the trouble of doing that proof. Even that first step I have here on my slide, defining a mechanization of your language in a proof assistant, as in defining what the instructions are, how the operational semantics work. For a lot of languages, it's not obvious at all how you'd go about doing that. But one language for which it's is relatively easy to do that is WebAssembly. Now, obviously, I don't think I need to introduce WebAssembly to this audience, but maybe I'll say what I like about WebAssembly. What I love is that it strikes a really, really good balance between being something that is widely used, widely cared about. It's not a toy language that nobody's heard about. It's something that actually has a lot of very invested users, but it also has a full formal specification. So it makes it relatively easier to do formal reasoning about this language. And indeed, sure enough, there's been a mechanization of WebAssembly in COG for years now. And we figured we might be able to build up on that to prove more interesting things. The property we were interested in is that the code in WebAssembly is organized in modules, and people care a lot about what's called module encapsulation. And what I mean by that is that a module should not be allowed to arbitrarily interact with another module's internal state, except if that module explicitly decides to export some of its state. And we were wondering if we could, building on top of existing mechanizations of WebAssembly in proof assistance, formalize this as a universal contract. The strategy we adopted was to use separation logic, and my team is big on this tool called Iris, which is a framework for separation logic that is implemented in the Coq proof assistant. And the way it works is if you describe any programming language by just giving the set of instructions, all of the operational semantics, etc., you can instantiate Iris, and then you get a bunch of proof rules that you get to write proofs in Coq about the behavior of your language in a separation style logic. I'll give an example a bit later. And we were wondering if we could use Iris on an industrial scale language like WebAssembly. And sure enough, a couple of years ago, we introduced Iris-Wasm, an instantiation of Iris for the WebAssembly language, the full WebAssembly 1.0 language. We took no shortcuts in doing this. There was one small area where we had to rephrase slightly one of the operational semantics rule from the standard just to accommodate for use in a proof assistant. But now we have a program logic for all of WebAssembly that you can use to write a proof about the behavior of a program that you've written in WebAssembly. On top of that, we've also defined a logical relation. I'll say a bit more about that later, but the important thing is that it helps you to reason about unknown code. Say you're calling a function from a library that you don't know or trust. We're still able to say meaningful things about the state of your program after you return from that call. And the universal contract that this logical relation captures is local state encapsulation. So we were really, really happy when we managed to get that all done in the Coq proof assistant. Now, obviously, you could think, you know, WebAssembly has local state encapsulation. Isn't that old news? Well, it's still, I think, very useful to have a formal proof of it, to have it formally stated, formally proved. But the thing that made us most excited is that now you can use it as a starting point to reason about all of the other variations of WebAssembly that are being proposed left and right in the research ecosystem, where it might not be as obvious that these properties are there. So imagine you define a new variant of WebAssembly that includes this new feature here. Chances are Iris has already been used to reason about that new feature. So you kind of have all of these areas of my Venn diagram here that already have work been done to them. So a lot of the time it might make sense to try and massage those together to have an instantiation of Iris in your new WebAssembly variant and to get that program logic, get a logical relation, establish a universal contract, and this way you can have a lot more insurance in what you've just defined. Now, I want to point out right away that even though I'm using a neat Venn diagram to represent this, it is not as simple as just taking the intersection of two things that already exist. There is a lot of work that actually goes into massaging these things together, because obviously when you work on real life languages, there's a lot of tiny details that wouldn't have appeared in previous works that use maybe idealized views. But it's doable. We've done it a couple of times. I'll give a couple of examples. But what's important here is that once you've done it, you get a lot in return. It's a wins for everyone situation. So I've mentioned before why the WebAssembly community should be excited about this. It was the thing about finding bugs, encouraging adoption. But the Iris community is also very, very excited about these works because we get to exercise the Iris program logic on a very large scale on these industrial languages, get the confirmation that this actually works on things that are not toy examples. It highlights maybe areas where Iris needs more research, where we could make advancements to facilitate some of the proof effort when done on real-world languages. And that new feature you've introduced to WebAssembly, that community might also be very, very happy to have that feature be studied at a real-life scale, to have Iris be adapted better to study that and to better understand how that feature exists, how the feature functions. Let me give two examples of how we've done this already. The first I'd like to talk about is a work in progress. Stack switching is a proposal of adding effect handlers to WebAssembly. And effect handlers have been studied in Iris before, and we're currently working on defining an Iris implementation of this stack switching implementation version of WebAssembly. So far, we have a mechanization of the full language, as well as a proof of its type soundness. Now, stack switching has been implemented already, so it's unlikely we'll find any meaningful bugs. But we have found areas where existing documentation about stack switching maybe was a bit imprecise and can be improved. And hopefully soon we'll be able to fill in this little center part and define that logical relation, have a universal contract. This is a work in progress, so hopefully we'll soon have something more exciting to say about that. But another example that is actually complete is memory-safe WebAssembly. That was a proposal a couple of years ago to add capabilities to WebAssembly as a way to, as a strategy of memory access. And likewise, we have leveraged previous works in Iris to define Iris memory-safe WebAssembly. And with the rest of my time, I'd like to focus specifically on Iris-MSWasm as an example to illustrate better how exactly this works, why it's useful, and why it's something that we're so excited about. So let me give a quick introduction to what memory-safe WebAssembly is. In plain WebAssembly, as I've stated before, we've been able to prove that we have local state encapsulation. A module cannot arbitrarily meddle with another module's inner state unless they decide to export something explicitly. The issue with that is that when you want to export your memory, your choices are you export everything or you export nothing. If you decide to export your memory as a module, then anyone is free to import that memory and do whatever they'd like with all parts of the memory. Sometimes it might be useful to have a finer-grained possibility to share at a finer grain, to just share small parts of your memory, but not others. And how can we obtain finer-grained memory safety? One strategy could be to use a capability. Now, capabilities can mean a lot of different things depending on the context. In the context of memory-safe WebAssembly, when I say capability, I mean a pointer together with some meta information about how that pointer is meant to be used. So that could be, say, a region of memory that I'm meant to be accessing. And if I try to use the pointer to access another area of memory, I'll get an error. And yeah, a couple of years ago, Alexandra Michael and her co-authors introduced MS-WasM, memory-safe WebAssembly, where loading and storing are performed not using I32s, but using a new type, a capability type that they call handles, that are these record types that contain 5 fields. The first 3, base, offset, and bound, denotes a region in memory that is meant to be accessed by the capability, as well as the address that the capability currently points to. And then there's these 2 last fields. Valid simply indicates if the handle is corrupt or not. And id is used to verify if a handle is still live, if it hasn't been freed. And so the way it then works, if I want to do a load operation, which I now call a segment load, seg load operation, is the rule that I have over here. The way it works, so if I try to load from a handle H, the last line is how you would expect a load to happen. I go into segment memory at the address specified by my handle, I read object C, and that's what I reduce to. Obviously, this is massively simplified. There should be deserialization and a lot of other things going on. But what's interesting here is these other 3 premises. These are dynamic checks that happen whenever I try to load or store, that are going to check that my offset is within bounds, that my validity bit is set to true, and that my handle is still allocated, has not been freed yet, using this handle ID. That was my last little field over there. If that works, then I reduce to what you expect to see. If one of those dynamic checks fails, then I reduce to trap instead. And importantly, we consider trapping to be safe because no memory violation has occurred if I trap in that way. And so when we saw this proposal, we were very, very excited about it. We think it's a brilliant idea. And we wondered if maybe we could do a bit better than just a pen and paper proposal for all the reasons we've mentioned before. And obviously, we were going to use Iris to do that. I've mentioned before that Iris has been instantiated with WebAssembly. That's Iris-Wasm. Iris has also been used to reason about capabilities. There's a number of works I could cite here. Cerise is probably the most famous one. And we tried to kind of massage those to get there in the middle. And again, despite what the Venn diagram might suggest, it is a lot more difficult than just taking the intersection of already known works. But we've done it. We've defined Iris-MSWasm, an instantiation of Iris in memory-safe WebAssembly. So that means we've introduced a formalization, a mechanization of the language in Coq. And even just doing that pinpointed a handful of small typos from the original paper, as well as a bunch of places where it was maybe a bit imprecise, just because it didn't describe the entirety of the module system. We have a program logic that can be used to reason about code written in memory-safe WebAssembly, and logical relation that can be used to reason about unknown code. So like So like in Iris-Wasm, that means if I make a library call to a function I don't trust, I'm still able to say meaningful things. And the universal property that now I capture in this logical relation is a much stronger one than local state encapsulation. It's robust capability safety. And as a last little thing, I'll show a little example that illustrates exactly what robust capability is and how exactly you could use these tools in practice. Let's have a look at an example. This is a program written in pseudocode in memory safe WebAssembly. I begin by importing an adversary function, fadv, that I know nothing about. I don't know the code. I don't trust the code. It takes a handle as an argument, returns nothing. Next, I'm going to allocate two handles, as in two areas of memory, h and h prime. I'm going to write a secret value 42 in the first handle. And now what I do after that is I call my adversary function with the other handle, h prime. And I expect that when I come back from that call, when the call returns, if I read from my value h, I wish to still see that 42. So if I put it in a variable g later, g should hold value 42. Now, this is a really interesting example because I do want to share some of my memory. I'm okay with sharing h prime, and I maybe want to share h prime, maybe I need to. So I cannot just say I'm going to wall off the entirety of my memory and just not share it. I want some form of sharing, but I still want to retain ownership of h. And so what I'd like to prove here is the whole triple written in gray here. If I begin by owning a global variable g, pointing to whatever, after this has all run, either I've trapped, or I still own that global variable g, and it now points to my secret value 42 that has not been affected by this adversary call. Why do I have a trap here? There are two places that I might have trapped. There's the allocation. The mechanization does represent realistic machine behavior where I might have an out of bounds and allocation could fail. Second place where it could fail, this adversary call, since I know nothing about what it does, it might well have a division by 0 or something. So I allow it to fail. Importantly, though, trapping is safe because no memory violation has happened before it happens. If you've done separation logic before, you might have some idea of how you would go about proving something like this. The intermediate steps look something like this. After I've done my allocation, I might have trapped, like I said before. But if I haven't trapped, then I still have that G resource, and I've now created new resources, one for H, one for H prime. Write 42 to H. Well, now my H resource points to 42. And now here's the interesting bit. I am calling my adversary function h prime. Again, I know nothing of the code of that function. I'll ask you to trust me for a little bit that I can make it to this stage here, where I still own h and g. I'll come back to exactly how that's done. The rest of the proof is now easy, right? I read from h, well, it's easy. I own h. I know it points to 42. Set global variable g. I just change what g points to. Free h. I forget those resources, and now all I have is g points to 42. But again, that really interesting spot was here when I called my adversary function. How am I going to reason about that? Our strategy was to use a logical relation. I'll give a very, very brief explanation of what a logical relation is. This is where it gets a bit more technical. The idea is to say, I will define what it means for a program to be safe to execute. I noted like this with a double turn style as opposed to single turn style, which means type checking in the type system. I'll say that this program is safe to execute, or you sometimes say it's semantically, it type checks semantically at type T1 to T2. And what I'd like to do is give this definition in a way that I'm able to prove the fundamental theorem for the logical relation that says that if a program type checks in the typing system, as in single turn style, type checks syntactically, then my program is safe to execute. It type checks semantically. The way I'll do my definition is separation logic style. I'll say that my program is safe to execute for type T1 to T2 if whatever value, if my value is safe to use for type T1, which I'll have to define in a minute, then I have this weakest precondition statement for the program. And what this means is the program plugged with the input value V runs safely, does not get stuck, and if it terminates on a value W, that value W is safe to use for type T2, my return type. Now I just have to define very carefully what it means for a value to be safe to use, and I should be able to prove my fundamental theorem. Integers are always safe to use, just because arithmetic is not a very dangerous thing to do. So I'll say that all of my integers are safe to use. Now handles, though, saying a handle is safe to use means I can do a load or a store safely. So I'll say a handle is safe to use if either its validity bit is false, meaning I'm never going to do an unsafe load or store because this is always going to fail my dynamic checks and it's going to just safely trap. Or if my validity bit is set to true, I own resources corresponding to the bytes in memory at the address specified by H. Last little caveat, I need any handle that is stored within those bytes BS to recursively also be a safer type handle. Importantly here, I'm only requiring resources for the area of memory pointed by H, not in the entirety of my memory. Last little caveat, trapping is safe, so I just end up by adding trap to my value interpretation. Defined this way, all of the instructions in my instruction set satisfy a universal contract. That means I can prove this fundamental theorem. So if you trust me that I'm able to prove that, I can do that last little step in the proof, where I'm calling my adversary function. Remember, the function has been imported. Instantiation in WebAssembly guarantees everything type checks syntactically, so I can apply the fundamental theorem. I know that my type checks semantically, I have a weakest precondition that I'm able to use to go from this step to this step. All I need to do is guarantee that H prime is safe to use, but that's fine. I own resources corresponding to H prime. I don't need the G resource. I don't need the H resource. I'm able to just carry them further into the proof. At the end, I know not much about H prime. I just know that it's safe to use. So it might point to something, or maybe the validity bit is set to false, but I'm able to carry out this proof in this Iris-MSWasm program logic. To conclude, we have shown in a number of ways that machine check proofs are possible even on industrial scale language definitions. Granted, WebAssembly is the low-hanging fruit, but it's still something we're very excited about. We think Iris is ideal to do this kind of exercise, and Iris-Wasm in particular is an ideal starting point for web extensions of WebAssembly in particular. There are 2 works in progress that I'm aware of that use Iris-Wasm. One is the effect handlers. I've mentioned that before. That's work that I'm currently doing with Sam Lingley in Edinburgh. And then there's a team at Northeastern University that's working on Iris-Wasm, and I believe Amal will be talking more about this this afternoon. But hopefully, we would love to have more people use Iris-Wasm, so hopefully this list will grow in the future. Thank you so much. I'm happy to take any questions.
Yes. Besides MS-WasM, are there any other like WasM variations that you're looking at right now in improving?
So besides MS-WasM, there is stack switching, the WasM with effect handlers that we're looking into right now.
And how do you decide, I guess, can you tell me how you like from inputters or provers' point of view, how would you decide for a given WasM variant what you are trying to prove about it in order to say it is safe in some way? How do you define
A lot
that
of times that's going to be fairly clear from what exactly your goal is when you're introducing the new variant. You know, when you introduce capabilities, then capability safety is a very fair is a very obvious property to prove. I guess for stack switching, maybe it's a little bit less obvious, and we're perhaps hoping that defining a logical relation will maybe show us what kind of properties will be interesting and easily provable. It's probably going to be something about control flow. Yeah, I guess a lot of the time it comes very naturally from defining the logical relation in
In
practice.
that, like trying to mesh what you're defining with the existing WASM safety contract kind of leaves some goals falling out of that. Is that what you're saying?
I mean, it's also very interesting to check whether or not we can still prove the invariance that WebAssembly, the plain WebAssembly, guarantees in new versions of WebAssembly. I guess that's something that's also very interesting. Are we able to guarantee the same things, or did we lose some properties by adding a new construct that maybe hijack control flow or behave a bit differently? So,
So
it's something.
that happens all the time in browser land, where a new API is added in, and then that invalidates some assumption that was made ages ago but not written down by anyone.
And I think that's also one reason why it's really interesting to do these proofs in a proof assistant, because the proof assistant is immediately going to flag that, like, oh, this one lemma no longer works. And this way you don't forget, you know, these assumptions. So I think that's another very good point and another good case for reasoning formally.
Thank you.
I can see there's a hand raised in the...
Yeah, your adversarial function could have accessed memory without using capabilities.
So the way things work in memory safe WebAssembly is that the only way to access segment memory is using a capability. So it's hard coded in the way the language works that you cannot use a normal load instruction to access segment memory. And that is an assumption that you have to make, that your implementation actually enforces that. But in the specification for memory safe WebAssembly, it is assumed that the only way to access segment memory is using a handle. You also assume that handles are not forgeable. But if those things actually hold in your implementation, then the adversary function would not be able to access that part of memory unless it somehow got its hands on the handle. And what we're proving here is formally proving that if I don't explicitly share it, they cannot gain access to it.
It seems like you've proved the assumption. What have you actually proved?
What we've proved
You've proved
is
one
that
of the assertions.
appear out of nowhere. As in, I appreciate how the property might appear trivial, because if you assume that a handle is not forgeable, surely a handle cannot be forged. But it's another thing to prove that the code given or the code executed by the adversary will not somehow violate that invariant. That it still is able to run and run safely and actually terminate without violating the invariant.
Okay, I'm still not totally convinced, but okay. Thank you.
Yeah, so speaking of existing WebAssembly properties and you know, making sure that they're upheld when we add new things to WebAssembly, this actually came up recently in the shared everything threads proposal. So WASM GC added these two properties of principal types and forward principal types. And it turns out that some of the new instructions and typing stuff we did in shared everything threads preserved principal types, but failed to preserve, until we caught it, forward principal types. And, you know, we caught it, we fixed it, but it would have been really nice to catch this earlier and or not even have to fret about it. Is there a path towards making you know, Iris-WasM easy enough to use that it could be a tool for the very early development of new proposals to make sure they don't violate existing invariants?
That's an excellent question. I think that's definitely somewhere we'd like to get at some point. Right now, Iris-Wasm is just so new that currently, sadly, it does require some expertise in COC and in Iris and in understanding some of these, some of the way it works to be able to actually use it. We hope that we would be able to make it more accessible, maybe automate some parts of it. That is certainly something we're aiming for, but it's not something that is very available at the current moment. And it's certainly one of the weaknesses of Iris-Wasm is that it does require some dedication to actually adapt these to new settings. It's not undoable though. There is another team that is working on Iris-Wasm that we're collaborating with, and we're very happy to see this interest. But it is something that they're spending a lot of effort to do, and it's certainly something that we can get better in.
Cool, thanks.
Andreas, in the chat. I guess not chat, but the video.
Is it my turn or what?
Yeah, your turn, Andreas.
Okay, thanks. Yeah, I just wanted to comment on Thomas' question, because actually the kind of things you reason about with Iris, so of course like programs, right? So the subject of your reasoning is programs and their execution, whereas the property you talked about is a meta property of the type system, so of the static semantics. So that is a completely kind of separate set of problems that is not really something that Iris is meant to address. That is about the dynamic semantics and execution of programs, right?
Mm-hmm.
That is a good point.
Just following up on that, I think the confusion Francis was having was exactly that. Just because you know that the system MS-WasM ensures that your capabilities are safe in some sense, doesn't mean that you know some particular program behaves the way you think. And that, I think that was the subtlety there.
Andreas, your hand is still up. Do you have another question or? Okay.
Oh, I thought I put it down. It's not up on my end, actually.
Cool.
Just following up on that quickly, does that mean that you could, along that line of reasoning, does that mean that you could think of this as like if you are writing the program like the one you showed before, where you're calling an adversary function and blah, 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 you want to check then these things are true at the end of it. Could you think of this as kind of like a unit test of the specification? In a way, like you have, like given this, given this program, these things should be true at the end. So we're actually checking to ensure that the specification that we've set it up correctly, that it enforces these properties. Is that a reasonable way to think about this?
One thing to keep in mind is that, so this is an illustrative example that I'm showing, but the big result that we have is the fundamental theorem for the logical relation, that as long as you're giving that minimal amount of information to your function, only, that it's input or safe to use, then you know that the function will actually execute correctly. So any code that type checks syntactically will actually execute. So we do have something that's, I think, a bit stronger than just a unit test. But
right, yeah, maybe that's a bit reductive in language.
Yeah, that's it.
Same intent of like, I have my specification that defines something. I want to make sure it ensures a specific thing, and I check that against that. Is that?
I think that's a fair interpretation.
Okay, just want to make sure I have the correct mental model of how this is.